In this presentation, I'll talk about how we can go about decarbonising our energy systems so that they can operate in a low or even zero carbon way in the future, which will make a major contribution to avoiding dangerous levels of climate change. Now, what do I mean by the energy system? Well, this is the series of processes involved in extracting fossil fuels from the ground, so that's coal, oil and natural gas, or alternatively harnessing renewable sources like wind, water and sunlight so that we can power our everyday lives. And by that I mean transporting ourselves from place to place, heating, cooling and lighting our buildings, be they homes or commercial premises, and powering our industrial plants that are responsible for producing our manufactured goods and also heavy industrial items like cement and iron and steel that we use in our cities and infrastructures. In this presentation, I'll first give a very quick overview of the sorts of impacts that we would avoid if we were able to limit temperature changes to those levels in line with international goals, and I'll then talk about the different processes involved in transforming our energy system from a very carbon-intensive present system to a low-carbon future system. And I'll specifically focus on the technologies involved in doing that. I'll then talk about some of the opportunities and challenges in making this very, very fundamental transition. I hope you enjoy this presentation. This first slide shows what the impacts would be at different global average temperature changes by the end of the 21st century, and it's specifically aimed at showing what impacts would be avoided if we're able to limit global average temperature change to 2 degrees Celsius above pre-industrial times, and that means the time around 1850 when the Industrial Revolution and the burning of coal in particular really got going. There's lots of information on this slide, but I'll just take you through it step by step so that you get a bit of a picture of what it's trying to show. On the left-hand side, there's a figure with 3 lines on it, and you can see from the vertical axis that it shows emissions in gigatons of CO2 equivalent. I'll just highlight that in yellow. And that's a way of measuring total greenhouse gas emissions, accounting for not just carbon dioxide, which is the most important greenhouse gas in terms of its degree of warming of the planet, but also other greenhouse gases like methane, nitrous oxide, and so on. So this measure is something which we show across the whole of the 21st century. So let's look at the horizontal axis, which runs from 2000 to 2100. And it shows, first of all, historically that emissions have been rising between 2000 and roughly about now. And then we'll highlight here about 2015, which is a point where the 3 lines start to diverge. What this shows is projections from 2015 of 3 potential pathways for global greenhouse gas emissions. If we look at the highest potential pathway, which I'm highlighting in yellow here, this is a pathway which is consistent with a no mitigation scenario, and that means no emissions reduction effort across the world and a continuation of using fossil fuels, much as we've been using fossil fuels to this point in time. Fossil fuels, coal, oil and natural gas account for about 4/5 of our total global energy supply at the moment, and so this shows that emissions would rise from approximately 50 gigatons of CO2 equivalent, that's 50 billion tons of CO2 equivalent, to over 130 gigatons of CO2 equivalent by the end of the century. Now it's fair to say that this projection is a little out of date because updated projections have taken account of climate policies and technological shifts which have been occurring in recent years, and they generally don't see emissions rising as high as that by the end of the century. The emissions that this shows would be, broadly speaking, consistent with a 5 degrees Celsius rise in global average temperature by the end of the century, and it is probably more likely that we're on a pathway somewhere between about 3 and 4 degrees at the moment, based on the current levels of policy effort that we have and also the current reliance on fossil fuels that we have. But nevertheless, this still proves useful because it shows what unchecked emissions and high levels of climate change might lead to in terms of impacts. The second line on the chart shows what would happen if we followed a pathway which is consistent with different countries' Paris pledges, and that's the pledges that different countries put in place in the run-up to the Paris Agreement being signed in 2015. This would limit greenhouse gas emissions to about 50 to 55 billion tonnes by 2030, which is the date which most countries put their pledges forward for in the run-up to the Paris Agreement in 2015. And what we've done here is we've just simply assumed that there's no backtracking on those pledges from 2015 onwards, and that the world as a whole therefore caps its emissions to that 50 to 55 gigatons of CO2 equivalent level going forward all the way to the end of the century. Now, climate modelling would suggest that that leads to about a 3 degrees Celsius global average temperature increase by the end of the century. And that is clearly not enough, therefore, to deliver the 2 degrees Celsius world. And so what we've done is we've finally added a third line which shows a route to achieving essentially zero greenhouse gas emissions by the end of the 21st century, and that would deliver a 2 degrees Celsius global average temperature change by the end of the century. So that shows what the left-hand figure is depicting, and then if we move to the right, you can see a series of impacts across the world as a result of those end-of-century temperature changes. And so these are impacts in 2100, and we show heat waves, cropland decline, flooding, and water stress. Now, I won't go into all of these impacts, but you can see, for example, that moving from a 5 degrees world in 2100 to a 2 degrees world in 2100, we would see cropland decline falling from about 7,600,000 kilometers squared, which broadly speaking is about half of global agricultural area at the moment, to something more like about 4,000 kilometers squared, so 4 million kilometers squared in a 2 degrees world. So by limiting global average temperature change to 2 degrees by the end of the century, we'd effectively be saving half of that cropland in the 5 degree scenario from declining. And you can see similar changes when moving from the 5 degrees world to the 2 degrees world across other impacts. Very notable savings in terms of flooding, where we move from 120 million people on average every year being subject to flooding in the 5 degrees world to about a quarter of that in the 2 degrees world, and about half of it in the 3 degrees world. And then another very big impact avoidance metric is around heat waves, where we move from about 12 billion people on average being affected by heat waves every year in 2100 in a 5 degrees world to much less, about 90% fewer people being affected in a 2 degrees world. So you can see a couple of things here really. There's first a lot to play for in terms of limiting global average temperature change to 2 degrees, both compared to 5 degrees and the 3 degrees scenario that we're broadly speaking tracking at the moment. And secondly, you can see that 2 degrees itself doesn't eliminate all of the impacts, and that doesn't mean that we just get out of the climate change challenge scot-free. It means that there's still a lot to be done. Keeping global temperature increase to 1.5 degrees Celsius has many benefits, even over and above 2 degrees Celsius. And this is one of the reasons why the Paris Agreement in 2015 moved the international conversation forward from envisaging 2 degrees as a safe limit to global warming to 1.5 degrees as a safe limit to global warming. And this is very well depicted by this chart. Let's look at warm water corals, for example, which I'll highlight now. This is the bar on the left-hand side of the chart, which is now highlighted in yellow. And the vertical axis, again, which I'll highlight, shows the global average temperature increase above pre-industrial levels in degrees Celsius. So it goes from 0 to just over 2 degrees Celsius. You can see that for warm water corals, the purple region, this depicts a real danger zone, and we are already seeing bleaching and loss of warm water corals, even at 1 degree Celsius, which is where we are today, broadly speaking. Just look at the right-hand side of this chart and you can see that over the period 2006 to 2015, on average, we've warmed the world by approximately 1 degree Celsius over and above pre-industrial levels. And that's already taken us into the red danger zone, if you like, for warm water corals. And as we increase our temperature beyond 1.5 degrees, beyond 1 degrees rather, then we get into a even more drastic area of danger for those warm water corals. And you can see other impacts such as the Arctic sea ice, which is likely to suffer much more regular and profound loss of summer sea ice as a result of warming temperature. So where you can see the purple around the 2 degrees line, that's indicative that we really want to avoid getting to that level of temperature change. And in fact, looking at all of these burning embers, you can see that a 1 to 1.5 degrees world is a lot safer in terms of the risks for these selected natural, managed and human systems. And that leads me to the first of my 3 key points, which is that climate change is not just one of many public policy problems, it's a central 21st century challenge, and it interacts with all sorts of other challenges as well. So we need to take this problem very, very seriously indeed. So we've seen that 1.5 degrees is an extremely important threshold which we don't want to go beyond. What does that mean in terms of our emissions of greenhouse gases? Well, we often look at the emissions of carbon dioxide in particular that are consistent with exceeding different temperature thresholds, and that's because even though there are lots of different greenhouse gases, there's a strong relationship between how much carbon dioxide we emit to eventual temperature change. And that's partly because carbon dioxide is a very long-lived gas that stays in the atmosphere for a lot of time, and it's also the most important of the greenhouse gases in terms of the share of overall greenhouse gases that it constitutes. So burning of fossil fuels leading to carbon dioxide emissions is really the main greenhouse gas emitting activity. So with that in mind, if we look at this figure here, there's a blue bar, and that shows that for a greater than 66% chance of limiting global warming to 1.5 degrees Celsius above pre-industrial levels, we've got about 420 billion tonnes or gigatons of carbon dioxide left to emit into the atmosphere, and that's actually measured from the 1st of January 2018, so over a couple of years ago now, which means that given that we've been emitting, as shown by the green bar, about 40 billion tonnes of CO2 each year, that takes the 420 down to something more akin to about 340 gigatons of CO2. And you can see, just focusing on that green annual bar, that from the 1st of January 2018, that gave us about 10 years at the rate of current CO2 emissions before we exceed with a 66% likelihood this 1.5 degrees Celsius limits to global warming. So that's a pretty big task. And you can see from a range of scenarios that have been run by the international modelling communities, and those have just appeared on the right hand side of the chart. Again, it's a similar chart to that from a few slides ago, where we show on the vertical axis a measure of total carbon dioxide emissions, and on the horizontal axis we show most of the 21st century. You can see that in the first period we've had steadily rising carbon dioxide emissions, but that even though there's a variety of different pathways to achieving a 1.5 degrees Celsius limit to global warming, most of them have this very rapid pathway down, actually to about 0 net emissions of carbon dioxide by 2050, which is the middle of the century, and then going to net negative carbon dioxide emissions, so net removal of CO2 from the atmosphere beyond 2050. So we're going to talk a little about how we might achieve that. So how would this happen? Well, on the left-hand side of this chart, there are 4 images, and they, very broadly speaking, reflect our energy system today across the world. So let's start with the picture in the top left of coal-fired power stations. We generate electricity primarily by burning fossil fuels, coal and gas, some oil as well in some parts of the world, and that's a very carbon-intensive process. It should be remembered that gas is a less carbon-intensive fuel than coal, but we won't achieve our ambitious mitigation targets by simply switching from coal to gas, because gas still emits too much carbon dioxide to meet the very challenging targets of limiting temperature change to 1.5 degrees above pre-industrial levels. Let's then move to the right and we can see a car there, and that's a typical internal combustion engine vehicle which burns petrol or diesel, so an oil-based product, for its motion. And then moving down to the bottom left corner we can see a house. This is a Victorian house which is probably not particularly energy efficient. It has thin windows and doesn't have cavity walls. It may or may not have loft insulation, probably leaks a lot of heat and then lets in too much heat in the summer. So that's a sort of typical house, particularly in the UK building stock. And then moving over to the bottom right, what we're depicting here is a coking coal blast furnace to produce iron and steel, and again that is a very carbon intensive process to produce one of those products that is extremely important in our cities and infrastructures, in other words steel. So that's the series of processes, or a set of typical examples of the series of processes that leads to a lot of carbon dioxide emissions in our electricity generation, our transport, helping us to live comfortably in our buildings and helping us to manufacture what we need. But let's now look at a right-hand side of panels, and that's a typical series of technologies that we hope to transition to in the future. So again, let's start at the top left of that panel, and now I'm referring to a top left of a right-hand panel. Let me highlight that so you know exactly where I'm looking. And those are wind turbines. That's an onshore wind farm, which is a very, very low carbon form of electricity generation. We can then use that electricity generation to power our electric vehicles. That's a picture of a Tesla, which is one of the companies that really popularized electric vehicles. If we then move down, we see something called a passive house, and this is a particular standard of house which has such a high level of insulation that it needs very, very little, if any, heating in the winter and very little cooling in the summer. So that can lead to extremely low levels of energy usage in buildings. And what energy is used is typically electricity, so it will use low carbon electricity generated from sources such as wind turbines and solar panels and so on. So it can be an extremely low carbon way of living. And then finally, looking at the bottom right corner, you can see something called an electric arc furnace for steel production. And again, that's a way of using electricity rather than coal to produce steel. In this case, that is through recycling scrap steel. So these are all alternatives which use low carbon electricity to perform essentially exactly the same services that we would be performing today, but with very, very few carbon dioxide emissions. Now I'd like to very briefly talk about something which I'm often asked, which is we often see depictions of the low carbon future and how that differs to the high carbon present, but how do we know, or how do we think that we know about this? And how do we translate that knowledge of the technologies that we might use to power our lives in the future into those greenhouse gas emissions reduction pathways? We do that using particular models called energy system and integrated assessment models. And those models do essentially one thing. They convert a series of assumptions into a series of outputs. And those assumptions cover the things that you can see on the left-hand side of this figure. So we have to provide as inputs into these models a view of socioeconomic development, and that means the rate of growth of the economy and population in different regions and across the world as a whole. We then need to provide assumptions of how that socioeconomic development will drive future energy demand. So what sort of vehicle kilometers will people want to drive in the future? How much will they want to heat their homes? What sorts of levels of manufactured products will they need as they get richer and as the world gets more populous? Then we need to provide the models with assumptions around what technologies will be available and how much they'll cost and what their performance will be. And by that I mean the sort of efficiency with which they will transform one type of energy, be that wind, water or sun energy, into electricity, or the thermal energy encapsulated in fossil fuels into useful energy like electricity. So we have to give the models assumptions about technologies. We then need to give the models assumptions about how much it will cost to extract different fossil fuels in different parts of the world, and we give them these things called supply curves, where there is a differentiated cost of extracting different amounts of fossil fuels depending on how deep you go or where you drill or explore for them. And then we finally often give the models intermediate emissions targets and policies. So there might be particular energy efficiency policies in different parts of the world, or there might be emissions targets for, say, 2020 or 2030, and we input those as further constraints into the model. So those are the 5 different elements that we tend to give these models going forward. And then what they do is they take all of that information and they perform calculations which in most cases provide us with what the models deem to be the least cost mix of technologies, fuels, and if they're capable of representing behavioural changes, those as well, that do 2 things, and they are that first meet our energy and socioeconomic needs, and secondly account for any emissions targets and policies that we've input into the models. So we can ask these models what is the cheapest or the least cost way, taking into account all of those elements on the left hand side going into the model, to reach a climate target like 1.5 degrees or 2 degrees, and they will, through crunching through several thousands of calculations, give us what they deem to be the answers. So that's a very brief overview that gives you a feel of what these models do and how. So models such as the ones that I've described show us that we need a fundamental transformation of the global energy system across all sectors of the economy, be that electricity generation, transport, buildings, or industrial manufacturing. And the pace of that must increase dramatically compared to the quite gradual way in which we've been replacing fossil fuel intensive energy technologies with renewables and low carbon alternatives. Now, the final point I'd like to make in this presentation is that we don't know what the future holds, and that much has become obvious given the coronavirus pandemic and the circumstances in which we find ourselves at the moment. This is a scene from Ridley Scott's 1982 film Blade Runner, depicting Los Angeles in the year 2019, so just last year. And whilst there are elements of it that have come to pass in reality in terms of large screens, there are obviously elements like flying cars which haven't. So it demonstrates quite well, I think, that visions of the future can get some things right and perhaps be overly optimistic on other things. And we need to really learn from that when we start trying to produce visions of how the energy system and the economy as a whole might develop towards a low carbon future. There are many unknowns and many things that we need to be aware of that might happen that we haven't planned for or imagined or envisaged. One really interesting example of that is what's happened to the costs of solar photovoltaic systems throughout the world over the last 10 years. This chart shows a blue line, which is how many groups involved in energy system and integrated assessment modelling envisaged that solar photovoltaic panel and installed system costs would develop from 2010 throughout the rest of the 21st century. And it shows an envisaged reduction in cost from $4,000 per kilowatt peak, that's the measure that's depicted on the vertical axis, down to about a quarter of that, to about $1,000 per kilowatt peak by the end of the century. And that was based on projections of how solar costs had been falling to that point in time and best guess estimates really of how fast solar costs might fall going forward. But we can contrast the blue line with the red line, which is how fast those costs fell in reality over the decade in the USA, which is one of the most expensive regions in the world for installing utility scale, so very large scale solar photovoltaic systems. And you can see the dramatic cost reduction of about 75% over the last decade. And actual latest data suggests that solar costs are now even lower than that in certain parts of the world, and that we can reasonably expect that solar costs will have fallen by another 50% or more by the middle of the century, and perhaps even earlier. So this just teaches us that we can often get our cost projections extremely wrong, and we can be overly pessimistic, because this is really a miraculous outcome, and it means that solar has become cheaper than many fossil fuel alternatives in many parts of the world, and that's changing the game in terms of electricity generation and the costs of using renewables and low or zero carbon sources compared to the traditional dirty fossil fuel sources. We've also seen a very rapid reduction in the costs of lithium-ion batteries, and this has made electric vehicles much more cost competitive with internal combustion engine vehicles. Vehicles such as the Tesla Model 3, which is shown in the top left corner here, are changing the market for many other vehicle manufacturers. So you've got companies like BMW shown on the top right, and then Volkswagen at the bottom, who are reorienting their product strategies towards electric vehicles, realizing that this is a new world of private motorized transport that we're moving into. And it's fair to say that this is all happening much faster than was envisaged about 10 or 15 years ago, when it wasn't really considered that electric vehicles could be a viable competitor, either in terms of range or cost or overall desirability, to the incumbent internal combustion engine vehicles. So this is another game changer that we have been quite surprised by, and so we need to reflect on what factors led to the rapid cost reductions and whether those can be repeated in other elements of the energy system. And there are all sorts of new technologies currently being developed which we don't traditionally incorporate into the computer models that simulate the evolution of the global energy system from its high carbon current state to a low carbon state. So looking at the top left corner here, you've got hyperloops, which were proposed by Elon Musk some years ago as a viable alternative to domestic aviation, given that they can provide very high speed terrestrial transport using renewable energy to power them. You've then got, looking at the top right corner, electric planes, which are being trialled by EasyJet and a number of other airline carriers at the moment. Looking at the bottom left corner, you've then got the fusion nuclear fusion reactors, which are being worked on by a number of groups throughout the world, and they could provide us with a huge source of reliable electricity at potentially very low cost some decades from now into the future. And And then finally, in the bottom right corner, you've got direct air capture of carbon dioxide from the atmosphere. So huge banks of fans, as depicted here, could pass very, very large volumes of air through them every day, and then using chemical sorbents remove carbon dioxide from that air and then sequester that carbon dioxide underground. So this could be a very important technology in terms of removing some of the carbon dioxide that we've already emitted into the atmosphere. This gives you a sense that there are technologies which are being worked on and behind which there's serious financing in all cases, which could be very, very important in further changing the game of our energy system going forward. This brings me to my final key point, which is that the future is very uncertain. There'll be a number of challenges, such as the current pandemic, such as the financial crisis, such as all sorts of other unexpected developments that we can only imagine, and some of which we just aren't even aware of at all, even in the furthest reaches of our imaginations at the moment. And there'll be all sorts of game changers as well. So ideally, we should plan our strategy towards a low carbon future using those technologies and policies which are as resilient as possible to a number of future uncertainties. There's much to play for and much uncertainty, but we can, if we keep our eyes open, plan in a sensible way so that we can achieve our zero carbon goals and limit global temperature change to 1.5 degrees Celsius above pre-industrial levels with the maximum likelihood possible. And so to conclude, just to repeat my 3 key points, climate change is not just another issue, it's a central issue, a defining issue of our civilization in the 21st century. And to address that challenge, we will see widespread changes across the energy system to avoid dangerous levels of climate change and meet our ambitious international goals. That will be extremely challenging given the pace of change required and the high degree and huge scope of technologies required across the energy system. But there are many opportunities, and there will be, as well as challenges, many pleasant surprises and game changers that will hopefully make the transition easier and cheaper and more attractive. I hope you've enjoyed the presentation, you found it informative. You can find out lots more about all aspects of mitigation, decarbonisation and other elements of climate change on the Imperial College Grantham Institute website. Thank you.